This example problem is number 83, found on page 33 of the textbook. The problem reads, you decide to launch a ball vertically so that a friend located 45 meters above you can catch it. What is the minimum launch speed you can use? How long after the ball is launched will your friend catch it? Okay, so we read the problem carefully. First we determine what we're looking for, what we're asked to find. You decide to launch a ball vertically so that a friend located 45 meters above you can catch it. What is the minimum launch speed you can use? So what is the minimum launch speed? So launch is the initial speed you're giving it up. So what is the minimum initial velocity, all right, that we can use? And it also asks, how long after the ball is launched will your friend catch it? How long? It's asking for time. So now, in this problem, it's asking for two quantities. Given, it says you decide to launch a ball vertically so that a friend located 45 meters above you. So, if this is where it's being launched from, this is your friend up here, this is the displacement, right? So we can call this maybe h, right? The height above. That's the displacement. So the height of the displacement is 45 meters. Now here's a little nuance. It says, what is the minimum velocity that can be used? Well, the minimum velocity is the velocity that can be used in which the ball goes up and it comes to rest. Its velocity equals 0 at h. And then it would turn back and come down, but your friend catches it. That's the minimum. The initial velocity in which its velocity here is equal to 0. Why is that the minimum? Well, if you throw it any faster, it will definitely make it to your friend, 45 meters above. It will actually rise up higher and turn around. But if you launch it with a velocity less than that, it's not going to make it. It's going to turn around before it reaches the height of your friend. So this is where our conceptual understanding of free fall is important. We can't solve this problem without it. That verbiage is very important. What is the minimum initial velocity you can give? Well, that minimum would be the initial velocity in which the final velocity is 0 at the height of our friend above us. The velocity can be anything greater than that. Initial velocity can be anything greater, but it can't be less than that. So that's the minimum. Because if the initial velocity is any less than that, it won't reach our friend. It'll come to a stop and then come back down before it reaches our friend. So, in that verbiage, in that problem, it's telling us that our final velocity at this point, the velocity of the ball at that point, at the height of our friend, is equal to 0. Okay? We also, its object is in free fall, so the acceleration is equal to g, 9.8 meters per second. I think that's all that's given. Right? So that's downward. Our h, our displacement, is up, moving up. So we're going to define a coordinate system. Let's say up is the positive y direction. So that means h is positive. The final is 0, so it doesn't have a sign. Or 0. Our acceleration should be negative because it's downward. Okay. So now, what equations are relevant? Now, I think the equations that are going to be relevant are the definition of acceleration and definition of average velocity. And maybe even the definition of velocity. Okay. So if we don't know time, so if you look at acceleration equals change in velocity, so v final minus v initial divided by time. We know v final, that's 0, right? That's 0. So this can be rewritten as acceleration equals negative v initial over t. But we reach a dead end there because we know neither v initial or t. This could come in use maybe later, but right here we can't go any further because we have two unknowns. We know acceleration, but we don't know v initial and t. Let's look at the average velocity here. Average velocity is equal to 1/2 v initial plus v final. And average velocity is equal to delta y. That's our displacement, which is h over t. So, if we look at these two equations, we know that final velocity is 0. So we can rewrite this one. Let me give some space here. One-half v initial. That's our average velocity. And average velocity is h over t. And so we can set this equal to that because they're both equal to average velocity. So we get 1/2 vi equals h over t. Oh, we have that same thing, right? Where we know h, we don't know vi, we don't know t. Two unknowns. But if we take this, I shouldn't circle our final answer. This equation and this equation are two separate equations that have the same two unknowns. This is a common technique to solve physics problems. If we have two equations with two unknowns, we can solve it via substitution. I'm going to erase this and pull this equation up here. Because both of these equations have vi, initial velocity, and t as unknowns. So what I can do is I can solve one of these equations for one of these variables and then substitute it into the other one. So this one's pretty easy. I'm going to solve this one for vi. So vi, initial velocity, is equal to 2h over t. I'm going to substitute that into for vi there. So I get acceleration equals negative, that negative sign stays there, 2h over t divided by t. 2h over, I forgot my negative sign, negative 2h over t squared. Alright. Now I have acceleration equals negative 2h over t squared. I know acceleration. I know the displacement h. I only have one unknown, time. So two equations, two unknowns. By solving one equation for one of the unknowns and plugging it into the other equation, what you do is you eliminate one of the two unknowns, and you get one equation with one unknown. So all we're going to do is solve this now. Let's multiply that over there and take the square root. You get t equals the square root of negative 2h over a. So I'm going to slide this over here. So we have t equals the square root negative 2h over a, our acceleration. T equals the square root of negative 2 times 45 meters divided by our acceleration is negative 9.8 meters per second squared. Once again, we see how the negative sign, the signs of our vectors are important, right? This negative sign was already there. It came from this negative sign there, because phi final is equal to 0. If we didn't correctly give our acceleration that negative sign because it's downward and we define upward as positive, then what would happen here? We'd be taking the square root of a negative number, and that gives us it's an imaginary number. It's not real. We need a real number for time. So, but these negative signs cancel each other out. So that's great. So time equals, so we have 90 divided by 9.8. Then we're going to take the square root of that. Where's the answer button? We get 3.03 seconds. That seems fairly reasonable, right? So time equals 3.03 seconds. That's how long it takes the ball to get up to our friend 45 meters above us. Now it asks us to find the minimum velocity, where we take our newly found time, and we can use an equation, one of these equations that has both initial velocity and time in it, and just put our time in there. This one's already solved for initial velocity. It goes 2h over t. Meters divided by 3.03 seconds. So 90 divided by 3.03 seconds. 29.7 meters per second. And it's positive. Right? It should be a positive because we're throwing it upward. That makes sense. So there are our answers. They both seem fairly reasonable. There's no reason for me to doubt. I didn't get 2 meters per second, I didn't get 200. That seems like a reasonable